Welcome to AP Chemistry. Take a moment to note the temperature and volume in the simulation provided. We will keep these values constant in the next few slides. Instead of helium, we now have 100 atoms of neon. The temperature and volume are still the same. Yet note how the particle velocity has decreased. The pressure, however, is still the same since the force applied per unit area is still essentially the same. Note how the pressure changes when both samples of helium and neon are added together. The total pressure is equal to the pressure of helium and the pressure of neon added together. This is because the temperature and volume of the container have not changed, and since the particles are being treated ideally, then there is no difference between the particles themselves. Thus, pressure is proportional to the quantity in moles. Dalton's law of partial pressures states that the total pressure is equal to the partial pressures of all the gases that exist within the system combined. Now, as we have discussed the relationship of total pressure to its partial pressures, let us now discuss the temperature in relation to the internal energy of our system. Recall that any change in the internal energy of our system will be due either to heat or work being done by the system on the surroundings or upon the system by the surroundings. In use, the internal energy of the system is equal to the total kinetic energy of all the particles that make up our system. If we take a given container, approximately 1/3 of the gaseous particles that make up the system will move in a certain axis. Now, pressure is equal to a force applied over a given area. Since force is equal to mass times acceleration, and acceleration is equal to the change in velocity over change in time, then substituting, force is equal to mass times change in velocity over change in time. Or, change in mass times velocity is over change in time. Since momentum, symbolized by P, is equal to mass times velocity, force is equal to change in momentum over change in time. Since change in momentum is equal to the difference of final and initial momentum, we can simplify the expression, since mass is constant, and thus change in momentum is equal to mass times the difference in final and initial velocities. Furthermore, since momentum is completely conserved in the collisions of our particles, the final velocity will simply be the opposite direction of our initial velocity, and the change in velocity is equal to negative 2 times velocity in a given axis. Substituting in, force is equal to negative 2 times mass times velocity over change in time. Finally, since it is not the force being applied by the particles, but the reactive force from the wall that we are measuring, And since every force produces an equal and opposite reactive force, force is equal to 2 times mass times velocity divided by change in time. Here, one must note the oddity of molecular particles, since the momentum of their collisions are completely conserved. In collisions in the macro world, this is not the case, since some of the energy in the collision will be converted to heat, i.e., the kinetic energy of the particles that make up that system. However, in the collisions that occur in the micro world, there is no loss to another. The very movement of the particles is itself the heat of the entire system. Continuing, since velocity is equal to displacement on a given axis over change in time, and since the total displacement is equal to 2 times the distance of x, velocity is equal to 2x over change in time. Solving for change in time, we now have 2x over velocity, and substituting and simplifying, force is equal to mass times velocity squared over x. Since pressure is equal to force over an area, and since the area of our container is x squared, substituting and simplifying, pressure is equal to mass times velocity squared over x cubed. Since the volume of our container is equal to x cubed, pressure is equal to mass times velocity squared over volume. Thus, PV is equal to mass times velocity squared, and 1 half PV is equal to 1 half mass times velocity squared. Since 1 half mv squared is equal to the kinetic energy of one particle, 1 half PV is equal to that particle's kinetic energy. For all the particles traveling in that axis, 1 half times the total pressure and volume is equal to the kinetic energy times 1/3 of the total particles. Thus, 3 halves PV is equal to the kinetic energy of all the particles in our system, or internal energy equals 3 halves PV. Finally, since PV is equal to nRT, internal energy is also equal to 3 halves nRT. Dividing each side by moles, the average kinetic energy is equal to 3 halves RT. Now, this only applies to translational motion, that is, the motion of gas particles traveling along a given axis, since this was the presupposition from which this equation was derived. However, we can also rearrange the equation to solve for the root mean square velocity of a given gas particle, using its molar mass, at a given temperature. In order to compare the rates of two gas particles flowing from a given opening, their root mean square velocities can be put in relation to each other and further simplified. Thus, kinetic molecular theory states that the gas particles of a given system are in constant motion and that their collisions are perfectly elastic, i.e., no loss due to heat. Furthermore, the average kinetic energy of the gaseous particles that make up the system is proportional to their temperature. Additionally, the particles move so quickly that the forces are considered to be negligible that they have upon one another. Finally, the last postulate is that the particles are so small that their own volume is considered to be negligible. The conditions at which gases behave most ideally, that is, according to the kinetic molecular theory, is at high temperatures and low pressures. However, real gases do not behave in this manner. At low temperatures, attractions become much more noticeable, and at really tiny volumes, repulsions become enormous. In order to correct for these, the van der Waals equation uses constants A and B for a given substance to correct for intermolecular attractions and the actual volume that the particles exist in. Till next time when we consider the mysteries of the absolute, Crip.